So here we're getting ready to get into the standard normal distribution, but before we actually get into that, let's talk about why we even need it. I posed the question here, how many normal curves are there? We've already talked about how a lot of things can be modeled by normal curves. The height of people, the blood pressure of people, salaries, any situation where most of the data is going to be falling around the middle. Most of the data is going to be falling around the average, and then you're going to have very few data that was exceptionally above average and very few data that was exceptionally below average, which is what's giving us that bell shape. So for example here, if you are familiar, hopefully you are, with the ACT test and the SAT test, which are two standardized tests that you may need to take in order to get into a certain higher level education, like getting to college or something like that. For instance, when I graduated high school, I took both the ACT and the SAT because I wanted to see which one I would do better on. But those two tests are scored very differently. For example, looking at these two bell curves here, you can see that the average SAT score is around 20 something, while the average ACT score is around 20 something, and the average SAT score is around 1,000 something. If I didn't have that curve there, and one person tells me they got a 21 on the ACT, and another person tells me they have 1,000 on the SAT, I don't know how to compare those two. I don't know how to say, well, I don't know, maybe you did better, maybe you did better. I'm not sure because I don't know what the comparison is between the scores of the ACT and the scores of the SAT. I don't know how people do on average. But with these curves here, now I can compare and say, well, if you got a 21 and you got 1,000, y'all did about the same because you're both around the average. So clearly, it looks like the average here for the ACT is actually 21. It's not 1,000 here. It looks like it's a little bit more than 1,000. Just keep that in mind. I'm just rounding these numbers about. But with that said, that brings up the point for the normal curve, because if I can standardize these scores, I can say exactly who did better, a 21 on the ACT or 1,000 on the SAT. I could do that if we had these scores standardized. So to answer this question, how many normal curves are there? There are infinitely many normal curves. There are infinitely many normal curves, and each of those normal curves has their own mean, their own center point, and they each have their own standard deviation, describing how spread out that data is. So that's not very helpful for us making comparisons, especially if we just talked about how the mean and the standard deviation are what determine the shape of that normal curve. Dealing with all these different means and all these different standard deviations is not going to be helpful. So what we do is we standardize it. We standardize it by saying the standard normal curve, or the standard normal distribution, will be the normal distribution with a mean of 0 and a standard deviation of 1. We learned back, I want to say week 1 or week 2, about z-scores, where z-scores describe how many standard deviations below or how many standard deviations above a certain person was from the mean. That is the random variable for the standard normal distribution. The random variable for the standard normal distribution is the z-score. And the z-score measures how many standard deviations above or below a value is from the mean. So if z-scores are telling us how many standard deviations above or below a data point is from the mean, here's just a quick illustration. Remember, in a normal distribution, the mean is centered in the middle. It is 0. That means that positive, in fact, let's use a different color here, positive z-scores, they had to be above average, because if the z-score is positive numbers are bigger than 0, it had to be above the mean. Negative z-scores would have to have come from values below the mean, or below average. And we can convert any x-score into a z-score using the formula that z, it's not the pen that I want, using the formula that z is equal to x minus mu divided by the standard deviation. So what I mean by that, for example, looking at this curve here, let's look at the ACT curve. Let's say that you score a 26. Your z-score would be about a 1, because we know the mean is here. This is an inflection point that is 1 standard deviation away from the mean. So if your x value was 26, your z-score would be about a 1. If your x value was 16, your z-score would be about a -1, because you're about 1 standard deviation to the left of the mean. If you fell about right here, you'd be a -1.5, because you're about 1.5 standard deviations away from the mean. And we will look at some examples of calculating z-scores and interpreting them in terms of the bell curve, but that was just a quick example of what's going on there. Positive z-scores are above average, negative z-scores are below average. So let's talk a little bit about probability as it relates to these z-scores. The cumulative area of a z-score is just a fancy way of saying the area to the left of that z-score under the normal curve. So for example, if I'm talking about the z-score of say 1.3, its cumulative area is whatever this area is I'm shading right there. It would give me the probability that someone had a z-score of 1.3 or less. Okay. So on the standard normal curve, let's say this is the standard normal curve here, has a standard deviation of 1. So I'm going to move this and just say this is mu, which is 0 in the middle. That's the mean. Has a standard deviation of 1. So you can see how much data is in between these standard deviations. So just looking at how I've spaced this out already, the cumulative area of -3.5, -3.5 is about right there. Its cumulative area, and remember, technically this curve never really touches the x-axis. It just gets very close to the x-axis, and then eventually, well, just stays very close to it. Doesn't really ever touch the x-axis. So the cumulative area at -3.5 would be whatever the area is under this curve out here. It's almost 0. So what I mean by that, at -3.5, this little sliver under the graph, that area is almost 0. Because remember, the total area under the curve is 1. On the other hand, as we continue to move to the right, so for example, the cumulative area of -2, I just sketched there in blue, which does include the green part. As we continue to move to the right, the cumulative area gets bigger as we continue to move to the right. For example, at 0, what would the cumulative area be at 0? Remember, this curve is symmetric. And also remember, what's one very important thing is that the total area under this curve is 1. So if we're symmetric and the total area under this curve is 1, then at 0, the cumulative area is a half, 0.5. At 3.5, which is all the way out here, the cumulative area is almost 1. That's almost the entire curve, is almost 1. So what that means, if the cumulative area at 3.5 is almost 1, let's put that in perspective. It is going to be very unlikely that you have more data. It's not going to be a lot of data that you have out here in purple. Most of the data is to the left of 3.5. And when I say most of the data is to the left of 3.5, I mean almost 100% of the data is to the left of 3.5. So in context, that means that there should be very, very few pieces of data that are more than 3.5 standard deviations away from the mean. That is going to be very unusual to have data that is more than 3.5 standard deviations away from the mean. That's what that's telling us there. So this lesson, all the examples that we're going to look at, which we haven't looked at a lot of examples yet, we've really just been getting the background that we need to understand the examples, but A lot of the examples that we're going to look at are going to be us calculating these cumulative areas, answering questions with these cumulative areas. And there's a couple of ways that we can calculate those areas. One thing we can do is we can use a table that's linked on Moodle. Table looks like this, the standard normal distribution table. There'll be some examples of us using this table to find areas. Another thing we can do is we can use a calculator. There'll be some examples of us finding cumulative areas with a calculator. And then another thing we could do is we could use StatCrunch. And there will also be some video examples of us doing StatCrunch. So we have 3 ways to find these areas. A table that you could look up manually, a calculator that you could type in a function, or StatCrunch.